Alright, are you ready for some more hash tables? So, the last things that we were talking about was the algorithms for lookup, insertion, and removal. Removal is not too hard. You just go to the index of the hashed key, look through the list there. If you find a pair with that particular key, you just remove the whole thing. Lookup is a bit trickier than we originally thought because it's possible that the key already exists in the list, so you got to search through the existing list to see if it's already there to change it. Otherwise, add a new node, and I'm sorry, that's insertion. And then lookup is just go and see if there's a value associated with a certain key, and that's that. So not too bad. Let's talk now about the complexity of using hash tables. And let me give myself some more room by putting this over here. So let's talk about first the worst case scenario. So in the worst case for running time, either the table is tiny or the hash function sucks. And this will cause a lot of collisions. So maybe here's my hash table. It's got like, I don't know, 2 indices, and it's going to store 2 million things. So maybe, I don't know, maybe this one gets 1 million, and this other one gets another million. A bunch of key value pairs there. Oof. So that's a problem. And so you have on the order of n nodes at each list index. So at least like n over 2 here, n over 2 here, or maybe they all get mapped to 1. But yeah, this is the worst possible case. So either for some reason you have a bunch of collisions. You have to search through on the order of n nodes, where n is the everything that you've inserted. Okay? I should probably say that somewhere. Dun dun dun. N is the number of key value pairs inserted. Okay? That's the idea. So this sucks. And so the running time complexity of insert, because it has to search for an existing key, it's going to be a problem. So hashing a value doesn't usually take too long. It depends on the type, of course. It might take a little bit of time, but let's pretend it's a constant, like your keys are integers. Then you got to go to a certain index of the table, which is fast. Then you have to search for an existing key in that table. So you go through this entire list, remember, see if that key matches with what you're searching for and inserting. And oh no, because you might have to search through on the order of n nodes, the entire running time for insert is linear. Oh no. And then changing a value or adding a node, that's super quick. That's again constant. So it's this search that is bringing us down. It's the bottleneck. Same for lookup. It's essentially do everything in insert, but just don't like change anything. Return the value if you found it. So again, everything is constant, but the search for the key. And if you got to search through on the order of n items, you have no choice but to have linear complexity. And then removal, again, you're searching, removing a node is constant to do. It's that search, again, it's linear time. And then space complexity, we'll talk about the space complexity of the table itself. No matter what, you're going to be storing n, some constant times n values, so it's like key value pairs. So usually it's like 2n maybe, who knows. The typical implementation of a hash table doesn't let the size of the table get too much larger than a constant multiple of n. So because you're already storing n things, and you have a table that's going to hold n things, you're going to get a worst case space complexity of O of n, which is honestly not that bad. You have to store n things anyway. So this is a really good worst case space complexity for a hash table. You're never going to store like a ton of extra indices, usually, unless like you don't make it resize. So I think in your lab you will just make a table, and that'll be your table. That's technically constant space complexity if you pick the number ahead of time, and you don't have as many nodes. So okay, let's talk about the average case now, because this is more fun. I told you that all this stuff is constant, and it's constant when things go well for us. So the idea is, in the average case, your values are going to be split up evenly across every index of the table. So if you have a table of size n-ish, you'll store a constant amount of things at each index, because in the average case, the number of collisions is very small. It's a constant number because maybe your table size is n, so maybe it's like size 2n is your table, and then you have n things to store. So on average, at each list index, you have 2n over n things, so the n goes away and it's constant. You see that? So that's super nice. You'll store a constant amount of things at each index, so maybe 2, probably less than that, if it's a really good hash function that you're using. So because search was the bottleneck for all of these operations, the running time complexity of all these operations now in the average case become constant, and you can't do better than that. This is beautiful. Constant lookup, constant insert, constant removal. Oh, glorious day. This is beautiful. So we can't do any better than that. And so yeah, in the average case, hash tables are amazing. Use them as much as you can. And usually, for space complexity again, the table is not going to be much larger than the amount of keys and values stored in it. So it's, even in the average case, going to be O of n space complexity, which you can't do better than that because you've got to store n things, no matter what. N pairs. It's always a constant number times n. So yeah, that is the idea of running time complexity and space complexity for the table itself, that is, in the worst case and in the average case. And oh man, do we like this average case a whole lot. So we're still talking about open hashing, and we talked about open hashing with lists. It's open hashing just means that at every index you're storing something that could hold other things. So that's all that open hashing means. At each index, you can store multiple things in some kind of data structure. We chose lists. That's a common thing to choose, but you don't have to use a list. What else could you use? Remember the bottleneck. It was this linear search to search through our list for an element. We were forced to do that because we used lists and we didn't pick any order. Well, what about a vector? And on top of that, what about storing a sorted vector? You'll read about this later, but it's n log n, log base 2 of n, to sort a vector, in the worst case, if you got everything there. So lookup is log of n, because you can use binary search. So you could bring down the amount of time that it takes you to do a lookup because you use binary search. But this makes it a bit worse for insert. So worse for insert, awesome for lookup. And removal. Possibly not removal because it's a vector. Sorry, it's awesome for lookup. So, darn. Well, there are faster data structures though. Come back to this, and we'll. I don't think I'll talk about this ever again, but once we talk about trees, I think if you had a very nice balanced tree that you could use at each index instead of a list or a vector, you get the best of all the worlds. You get log of n everywhere. So that's the idea. Just want to leave you with that. And I have to go have office hours in a little bit. Let's start a little bit of closed hashing. And so let's remember what this means. When you use closed hashing, it means that you have to use the indices of the table, and that's all you get for collision purposes. which means if this is your table, like it was supposed to go here, you need to put it in one of the empty places, okay? And that's a big decision to make. So if you decide to keep everything in the table for closed hashing, where do you put the values that collide? You have to pick indices, and there are a bunch of different strategies for that. So you have to pick an open index. Closed hashing is also known as open addressing, which is the worst thing that they could also call it. I am so sorry. This is why it's very confusing. Closed hashing, open addressing. Then you have your open hashing, aka separate chaining. Let's just stick with one or the other. Okay, I'll call this closed hashing. Okay, on now to how we can solve this. So one way to do it is to use this idea of linear probing. So if the hash function sends you to one location, you have to pick another, obviously. You have options. Linear probing, the option is the next empty bucket in a linear fashion. So let's say that here's your hash table. It's got some indices, and I don't know, let's give it some more actually. Let's say that the hash table sends you to I want one more actually. Let's say that the hash table sends you to index H, but that index is already populated with a value. It's got like 42. And then so is the next one, 43. Well, you would end up trying this one that's open, okay? So that's the idea. You'll try H, you'll try H plus 1, H plus 2, in that order until you find the next empty bucket. Now remember, bucket is just another index into the hash table. So you will put your key, or you'll put your value and key, actually, at H plus 2. Say that you're trying to map, I don't know, 87, and that goes to, I don't know, 88. So you're going to put your 88 here as the value, but you'll also put the key. So these really also have their keys as well. So it's like, I don't know, 0 went to here, 7 went to here, and 87, that key went to here. Okay, so you still are going to store keys and value pairs, but you're going to store them inside the table, linear probing, and you're going to search in order. So if 87's hash took you to H, unfortunately H was being used, so you'll try the next one, then you'll try the next one until it's free. Okay? So that's how that works, and you'll wrap around the vector if necessary. So if you ended up here and there was something there, well, you'll have to wrap around to the next location at the start of the vector now. Okay? So just keep that in mind. And yeah, so you will need to store the number of elements in the table as well as the size, because you might be sending yourself on a wild goose chase otherwise, because maybe the entire vector is full, the entire table is full. Obviously, if the table size is n, the number of elements inside the table is already also n, then you'll never find a new index. You'll just keep searching next one, next one, next one, and it will be fruitless. So just keep that in mind. Make sure to check for that, and you will need to resize if that ever becomes the case. So that is linear probing for you. You are still storing key value pairs at each index in the vector, but you're not storing multiple. Okay, you're finding a new index for yourself. Okay, so that's all well and good. There is a problem with this naively. So let me try and copy all of this, and let me try and show you the issue here. So this is fine. If I go and I want to look up my key 87, well, it'll send me to H, and that'll be like, okay, this was 0 as the key, that's not 87. This was 7 as the key, that's not 87. There's 87, I will return the value 88. That's the normal operation. But what if we come along and we say, oh, delete key 7. that's going to be a problem for us, because empty space, this will now be empty, now empty. And the second you have empty space, you're like, oh, it wasn't there, because that's your stopping condition. So empty space ruins lookup. Okay, if you see an empty space, it means that you didn't find the value you were looking for, because you would have put it there. So you need to mark this somehow. So mark. This motivates a second kind of emptiness. That you have your empty from the beginning, empty since start, as your book says, and then empty after removal. So if we change this to say empty after removal, maybe, EAR, empty after removal, then when you go and you search for your key 87, you'll get sent to this index. You'll be like, ah, 0, no. You'll get to this one, it's like, oh, I've deleted something, I'm allowed to continue searching. And then you'll get to this one, it's like, ah, there's my 87. Everything's all well and good. So you're going to have to store a different kind of emptiness to make sure that you don't stop looking. Yeah. Okay, so that is a big deal for this kind of closed hashing / open addressing. Confusing. All right. Your other options, we're trying to choose indices that are not going to be likely to have a bunch of collisions. And unfortunately, linear probing has a bunch of collisions. Say, remember that 12 example, for example. The second you have a bunch of things hashing to the same hash, you're going to start chaining them right next to each other. There's that one, there's that one, there's that one, there's that one. And the next empty spot is going to be way over here, maybe. That sucks. We need to try more empty spaces that aren't right next to each other. This is a bit of an issue. All right, so one of the ways to solve that is to use what's called quadratic probing. So instead of going from index h and then the next one we try is index h plus 1, well, instead pick two constants, your favorite numbers, c1 and c2, and I is just where you're looking. So you start at 0, I equals 0 to begin with, then try I equals 1, then try I equals 2, as long as you're not finding a new spot. And so when I is 0, the first thing you check is h. Okay, hopefully that makes sense. So you're still going to try h first. You'd be like v. First you'll try h, because that's when I is 0. And they're like, oh, okay, there is something there. So I'm going to try, let's say that c1 equals 5 and c2 equals 7. You will try then next, with I equal to 1, you'll try h plus 13. So you'll skip a lot of space. That's the next place you try. And then maybe down the line, what's the next one? That would be your I is 2, so it's h plus, I'll just write it out actually. It'll be h plus 5 plus 7 times 4. Wherever that takes you. Okay? So if that one's also full, you'll keep trying that one. And so this will, again, wrap around. If it gets too big, you'll just use mod. But this keeps you from having a bunch of places that are used right after one another. Okay? So that helps to kind of break up large clumps of buckets that are used right next to each other. Keep used buckets from clumping together. Okay, C1 and C2, those don't change. Those are just your favorite numbers that you pick. I don't know the best place to put these now. I guess I'll have to delete them. So that is quadratic probing. It keeps things from clumping together. And then mathematically, you can eventually come up with reasons why this also leads to some issues. So then people came up with this idea of double hashing. So you have now two different hash functions. And remember, a hash function is just a function that takes some key, whatever type it is, to an integer value. And here is your new sequence that you're going to try. It's called your probing sequence. Okay? You will start with h1. That's like your normal hash function. So when I is 0, you'll just try h1 of the key. Okay, so this will be the first thing that you try. For whatever you want. First, you'll try h1 of your key. See if it's taken up already. And if it is, well then the next thing you'll try is not some linear combination of two constants and the hash function's value again. It's going to be hash your value with a separate hash function, one that behaves differently. And this will give you even more variations. Okay? Dun dun dun. And then, okay, so the next one you'll try would be h1 of key plus I is now 1 times h2 of key. And that's super nice because h2 might behave super differently. And it'll behave differently for each key, which is a bit more than C1 and C2. Those will behave the same because they're constants. Okay, so it's kind of breaking up the monotony even further to try and space things out in your table. Okay, so this will, in theory, give you the best result if you choose two good and different hash functions. And yeah, that is all you need to say, I think. Let's see, how are we doing on time? I think I am going to recreate our idea from last time with the lists, and I'll do it for closed hashing. How about that? Okay, so let me give you an example of the middle of the road. Let's do quadratic probing instead of linear or double hashing. And I have made an example for you called closed hashing, and let me just go through it with you. It's a lot of work, a little bit. So that's why I don't want to type this in front of you. So we're going to store pairs in our table. Our table is going to store just pairs, okay? Because we're going to find a new index for every pair, for every value, okay? Every separate key value, I guess. Something like that. So my hash table looks like that, and I've chosen for C1 and C2 5 and 7, and my hash table size is 11. So still we have a silly hash string function, a hash function for strings, and our pairs store extra stuff now. In addition to the key and the value, which are always necessary, I will save, has this element that I'm about to look at in my table, has it been deleted already? In which case I need to continue searching, right? Also, is there a value here right now? In which case, it may be something I need to check. Okay? So inserting into hash table, here's what we do. We need to find a new spot. Okay? We need to find the spot to put our key and its value. So I'm going to first start with h, which is just the hash of the key, and the index, this idx variable, is again what I'm going to be using to search through. So eventually idx will be set to a value that I can insert into. Okay? And I'll start my I at 0 because this involves I. Okay, so I'm first going to look at just h, index h. All right, and then, all right, how do I find the index that I need to insert at? I'm going to use this while loop. So while the index that I'm trying to look at, the one I'm considering, while it has something there, and that thing that it has there is not equal to the key, I'm going to keep on advancing my index to be the next one that I want to search through. Okay? So you keep on doing this until you find a spot. Okay? And eventually, this while loop will stop. So when this becomes false, that means either we found an empty spot, either that one is false, or this one was false, which means we found the key that already existed in the table. Okay, we need to overwrite it. So either way, we can just do the same 3 lines. We can say, all right, key is set to the key, the value there is set to the value, and the fact that there is a value here right now, yes, we just put 1 there. Okay? And now lookup is very similar. We need to find the spot to search through. Okay, so initially we start at index h again, and then keep on trying while there's something there, and we can look at it, and its key is not equal to our key. So eventually, at the very end, again, when this becomes false, either it's empty space, in which case we need to return -1, we didn't find it, or this was false, and the key is something that we just found. So if it's equal to the key, then we need to return the value there. Okay? Not too bad. It is a lot going on, I know. So that's why I'd prefer for you to do the open hashing for your lab, but this is a good example, I think. Now, in the main function, this is just the same stuff as before. Make a hash table of a bunch of pairs now, not a list of them. And insert the stuff, look up, and then insert something that already exists, so we'll overwrite it. Okay? And if we go and rerun this, I was just practicing with myself, we get everything that we got last time. Okay? So this is just another option for hashing, all right, without lists. So that was an example of quadratic probing. Okay, so that essentially brings us to the end of the implementation of a hash table. The only thing you ever have to care about now is maybe your hash table gets too big, okay? In which case you must resize it, just like a vector, all right? So eventually you're going to get full, or you start having a ton of collisions. In either case, you need to resize your hash table. It is a vector, so just like for vectors, you're going to copy everything over, maybe double the size if you need to, things like that. So this actually, in the average case, just like for vector, and this is beyond the scope of this class, it doesn't affect your time complexity in the average case. As long as you don't resize too often, as long as you just keep doubling it whenever you need to, which is fun to think about. Please come to office hours and I will tell you why that's true. It's some math. And so usually what you do with a hash table is you resize it to a size greater than or equal to 2n, your current size, and that is the next prime number after that. Okay? So prime numbers are nice, remember. And we keep track of when we need to resize based on this idea of a load factor. So a load factor is the number of items in your hash table divided by the number of buckets you have, so the number of indices available to you. And what you do is you resize when this gets above like 0.75, this ratio. Okay? So it's getting a little too full, let's resize it. Okay? That's the load factor. And yeah, that is all you need to know to implement your own hash table, and I've given you some starting points in code. All right, so now, before we end this, let's talk about C++'s implementation of it. It's called Unordered Map, and if you remember from your lab, you practiced with both of these. What does this mean? But, oh, okay, whatever map was must actually be ordered then. And yeah, remember that hash tables are all about there is no order. You're just putting stuff and it's going to the index that the hash sends it to. You're only getting to look up things. So let's go and poke around those documentation files and take a look. So here we are in the, no, I was playing around here too. Unordered map, fancy stuff. You only need to care about the key and the value. So the type of the key, then the type of the values, and the rest are usually filled in for you. Okay, you don't have to worry about them. They have default values. So, as an example, you can have, oh man, they use type defs. You can have a hash table of taking strings and giving back strings. Okay, that's the idea. And to add stuff into a hash table, you can say .emplace. You can also use @ if you wanted to. But in place, you give it a key, you give it a value that you want to put there, and it puts it in there for you. You can say @ to get an element if you know it exists. You can say .at and either set the value, get the value, print it out, whatever you want. And you should make sure, though, that the place you're trying to access has something there. So you should use count, usually. You'll say count, hey, does this key exist in the hash table right now? And so you'll always be checking things like, hey, is the count 1 or not? It'll only ever be 1, right? Because you'll only ever have one key mapping to another value. But yeah, that's the idea. Let me show you it in action, and we'll go from there. Let's see here. I guess I kind of want to copy most of this, don't I? Edit. Unordered map example. So most of this stuff I can keep the same. All this stuff is going to be done for us, though. Whee! Super nice. So all I need is unordered map. And string, of course. So now, I'm going to make an unordered map to do all the same stuff. So unordered map, and I give the key type, which is strings in our case. And I give the value type, which is ints in our case. And I'll call it, I guess V is just as easy. And here I'll just replace all this stuff with the actual code for it. So instead of insert in the hash table, we'll say v dot in place. You know what? I might as well call it m, since I'm changing everything anyway. M dot in place, mom, that one, and do the same for me. And now to look up, the way you do it is you say if m.count mom is greater than 0, oh, then we know it's there. Technically, we already know it's here, but it's a good way to do this. And you'll say cout m.at mom, and this gives back the value stored at that key. I'll do the same for me and my cat. Okay, and then we can update, of course. We can say, all right, we can put it in there again, like this, and then one more time we can do all this again. So that is a hash table for you, and it looks like I forgot a semicolon. Hello. Forgot 2. Are you happy now? Oh no, forgot 3. That's one nice thing about this auto format. It catches those errors. It makes things look weird when something's wrong. And, oh, forgot to delete those. There we go. And what do you know? Everything's there, except for this one. This one didn't work for some reason. So, let's go back to the documentation. Inserts a new element if the key is unique. Only takes place if no element in the container has a key equivalent to the one being emplaced. Oh, okay. We can't use that then. We have to say at. Okay, if it's already there, we have to say at. That is the lesson. Okay. And that should do it. If it wants to save, I may have just frozen my Vim. Okay, now it's happy. That's better. Okay. So that's everything, and that's all that I wanted to say there. So it has an iterator, in fact, if you want to iterate through it. Let me go to the documentation again. It has like a begin and an end. Again, this is just up to the container itself. It's going to go through all of the indices, and it will just map through them. So let's watch it work, and we'll see how this happens. So what it's going to give back is an interesting iterator, I think. Now, I guess we'll find out. We'll find out what's there. What does n give us back? No, it just calls it iterator. That's not helpful for us right now. Iterators are pairs with first and second. Okay, that's all we need to say. So if we get back an iterator, we can say dot first and dot second. That's the key, that's the value. Okay. We can say unordered map. Remember that you can do this with auto. String int iterator it equals m.begin. It is unequal to m.end it plus plus, and now star or it arrow first is the key, it arrow second is the value. All right, so now we'll print them all out. We'll say cout it arrow first, which remember is equivalent to star it with parentheses dot first. Now we'll do like an arrow it second, new line, and yeah, that's all I want to do, I think. Oh, did it not save? It's really unhappy. Hello, Vim. Well, we'll see if it actually saved. It may have not. Okay, there it worked. Yay! And so it's got stuff there. It looks like I didn't find my cat. Oh, that's because I didn't put it in there. Okay. So that is looking good. Alright, it's got Lawton, maps to that, mom maps to that, and so it went in a weird order, but that was its order. Okay. And honestly, I need to go and check my time. I don't know if I have enough time to give you this fancy example right now, so I will be right back. Okay, yeah, there's nowhere near enough time, so I made it for you, and hopefully I can explain it. And if you're curious about this program, please come to office hours, and I will be happy to explain it. It would take probably an entire class period to understand all the reasoning behind it, though. So this is going to be an autocomplete program for Shakespeare. So I'm going to give my program the entire works of Shakespeare, and it's going to produce words in the manner that Shakespeare might have written them, which is really fun. It's a machine learning problem, actually. So this is our first machine learning example, if you're into that. So the problem is, given the previous two words, so if you save those, and you're like reading a long string of text, so look at the previous two words and use that to predict the next word that might be used, that might be written. So for example, if you read the sentence, if your program that is a machine learning program reads this sentence, the quick brown fox jumps over the lazy dog, it's going to look and keep track of the previous two words always, the quick, then quick brown, then brown fox, then fox jumps, and then based on those two words it's going to remember the word that came after. So, and that'll use that to predict. So the next time it sees the quick, it'll predict brown, okay? And the next time it sees fox jumps, it will predict over. And the cool thing about this is you can predict multiple things because you may have seen the same two words before. So here's my example sentence. Oh shoot. A, B, A, C, A, B, D. So if you see after learning this sentence, if you ever see A, B again, you can predict either A or D because you know that the writer of this sentence chose both of those. A could have come after or D could have come after. Okay? So that's the key idea. You save the last two words, like the last word and the last word, and then a vector of possibilities to use for prediction. So this is the final type, a pair of words, and then map that to a vector of strings. I'm not going to test you on this. It's just a really cool example. I want to show you it working. And then you will randomly choose from the next, from the vector to predict the next word. So like if you had A or D in the vector, you'd randomly flip a coin and pick one or the other, and then use that to be your next word. And you can predict based on that. Then the next word that you spat out is your last word, and the last word becomes the old last word, things like that. Feel free to study this program, and I'd be happy to explain it. This is recording, right? Yeah. So here's my program. Here's my pair. So my pair of words, the last word and the last word that I've seen. Those will be the keys of the hash table. And then to use unordered map on a type that I made myself as a key, so I have to tell unordered map how to hash it. You have to give a fancy class that has a operator parenthesis that tells you how to hash it using the strings inside. And it also needs to know how to compare for equality, because if you think about how you need to implement a hash table, you need to do both of these things to see if you found what you were looking for. And then we'll convert all the strings, all the words inside of Shakespeare to lowercase so that we'd have more opportunities to predict things. And then this is the main program. It's under 100 lines, actually, which is surprising. And it predicts words. It talks like Shakespeare might have talked. Makes brand new sentences. So first we're going to read from the file. We're going to read the last two words and try and predict the next word based on that. So we're going to save inside of our fancy completion map that information. Okay, so at a certain key, which is the last two words, we're going to add add the next word to the vector if it exists. We'll push it back, otherwise just make a brand new vector. I realize this is not enough time to explain this, but I hope that once I show you this running, you'll want to look at this yourself. And then once you've made your map, your completion map to predict things with, you go and you pick a random key to start with, and then you use that to generate a random sentence. Okay, so I'm going to pick a random starting word, or starting pair of words, and then I'll just write a length 100 sentence, so 100 words. And so starting with those two words, I'll predict 98 more, and it's possible you'll need to stop early if you've never seen these last two before, but usually that won't be the case. And so then you'll just predict using the completion map. At each, for the last two words, you can go in and get a vector, all the possibilities of the next word, and then you pick the next word randomly, and that'll be the next word in your sentence, and then your last two words change based on that new word that you added. And then finally, you can output the sentence that you built up. So it's really fun. You're just keeping track of the last two words and the possibilities of the next word that came after it. And you can use that for prediction. Super cool. Let me show you it working now. I'm going to run it with Shakespeare.txt, which is the entire works of Shakespeare. And when I hit enter, it's going to make a random sentence that the world has never seen before. So apparently, after step fourth, the word to was a possibility. Apparently, after to whip, hypocrisy, comma, was a possibility. After force should cease, period, was one of the possibilities. But this is like, it makes funny sentences because it kind of makes sense but doesn't, because only the last two words predict the next one. Okay? Isn't this cool? And you can run this and get completely different sentences each time, but that the moon winks. And they're all like sensible but also senseless, which is really fun to think about. Yeah. So let me do two more, and you can read these, and hopefully you'll want to now go and analyze this program and see why it works. But this is a great example of hash tables. It is a good culmination of everything that we've been learning. Yeah, I think that's all I want to say. What art thou indeed? All right. Some quick exercises. I think it would be a very good exercise and a good preparation for your next lab to create your own hash functions for all of these different types. So try and think of another way to calculate hash functions for integers using more than just the modulus operation. Do the same for doubles and strings and characters and vectors of those things. What? So at the end of the day, you need to turn all of these types into numbers. And for like the case of my computer just froze. I hope that you can still hear me. And yeah, so how can you turn those into numbers? And one way to do it would be to convert everything first to a string. Okay, because then you can always convert a double to a string, you can always convert an int to a string, you can always convert, well, technically it's made up of characters, but you get the idea. A vector of whatever you can just convert to a string with a bunch of commas in between all the values, right? So think about that. That's a good avenue forward. And then you can hash the string. So if you come up with a good way to hash strings, you can hash everything usually. Okay, so that's where I want to leave you there. And before I let you go, I want you to do these mid-semester evaluations. So it's week 8 now, and so the semester's like 17-ish weeks long. So we're pretty much in the middle, and I would like you to fill this out for me. It's an anonymous feedback form. I'll prove to you that it's anonymous. It's on Canvas. Oh, sorry, I gave you CSCI 40s, but they all look the same anyway. Here's my proof that they're anonymous. Keep submissions anonymous. There's yours. Anonymous. There we go. And yeah, I just want you to go through and fill this out if you have time. Obviously, I'm not grading on it, but it would really help me. The college is going to send another out for you, like that one's for them. But this one's just for me. I want to look at it and see if I can improve the class. Well, you still have a chance to benefit from that improvement. So please go ahead and fill this out if you can. If you have some time, I would really appreciate it. It would help me make the class better for you and for my future students. So that is that, and because it's anonymous, you can say whatever you want, right? That's the idea there. So that's everything that I wanted to say. Enjoy the Shakespeare, and I will see you in your lab.